Welcome back, Chemistry 30. This is the 19.4 neutralization booklet, the last booklet in the acids and bases section. So in this section we'll be looking at neutralization, salt titration, equivalence point, acid-base indicator, and endpoint. Write chemical equations for neutralization reactions. Explain how neutralization reactions are used in acid-base titrations, and solve mathematical problems involving data from titrations. First of all, neutralization is when an acid combines with the base to make a salt plus water. And by salt, what I really mean here is ionic compound. Metal combined with non-metal. So for example, hydrochloric acid plus sodium hydroxide gives you water and the ionic compound. The cation comes from the base and the anion comes from the acid. So the beginning part of the base, last part of the acid. So if we look at a couple of examples of that, sulfuric acid and sodium hydroxide. So sulfuric acid, H2SO4, sodium hydroxide, NaOH. So of course we'll have the H from the acid and the OH from the base combined to give H2O. And Na and SO4. Na of course is +1, SO4 is 2 minus, so we have to have two sodiums there. Na2SO4. With that we'd have to put a 2 in front of here, which will give us a total of 4 hydrogens. So if we put a 2 in front of there, we'll get our 4 hydrogens as well. Nitric acid and potassium hydroxide. Maybe you try that one right now. Pause the video. Write down what the equation is. If you had a chance to do that, nitric acid is HNO3, potassium hydroxide is KOH. So of course we have H and OH to give us water, and K and NO3 to give us potassium nitrate. Titration, you'll be doing a lab on this. A method for determining the concentration of a solution by reacting a known concentration of solution with a solution that is unknown in terms of concentration, and the whole process is called a titration. So there's a few steps for that. Measure out a certain volume of the unknown base or acid and have it in a flask, like right here. So it could be an acid or a base, it's unknown concentration. Then you have a device referred to as a burette, which is a tall, narrow column that you can easily read the volume from. It's filled with the solution that you know the concentration of. So if I have an acid here, I'd have a base that's known concentration. Or if I had an unknown base, I'd have a known acid of the concentration that I would know. Add this until neutralization occurs, and then from there you would be able to calculate the unknown concentration by looking at when the reaction is complete. And of course at neutralization what happens is it's referred to as the equivalence point. The moles of hydrogen and the moles of hydroxide should be equal. And we could figure out when that happens by using a pH probe or a visual cue, a visual indicator, which serves as to inform you when this happens. So equivalence point is when this is equal. An indicator will hopefully find that, and it's referred to as the endpoint. So we're hoping that the endpoint is close to the equivalence point. The endpoint being the visual color change that we see that informs us that the reaction is complete and that neutralization has happened. And of course, obviously, you'd want to choose an indicator that has an endpoint that's close to whatever the equivalence point is. Okay, so we'll look through a couple of examples here. So the first one, in a titration, 33.21 mils of a 0.3020 molar rubidium hydroxide solution is required to exactly neutralize 20 mils of a hydrofluoric acid solution. What is the molarity or concentration of the hydrofluoric acid solution? So first of all, you need to have the balanced equation. So this is a nice one because it's a 1 to 1 to 1 to 1. HF plus RbOH yielding RbF and H2O. And it would help if you write down the information underneath. So here the hydrofluoric acid is the unknown, so it goes in the flask. The rubidium, its known concentration, so it goes in the burette. And we were told that we have 20 mils of this unknown, and it takes 33.21 mils of this, which has a concentration of 0.3020 molar, to neutralize it. So we're asked to find this. So there's basically 3 steps. Back in Unit 2, we talked about C equals N over V. The concentration is equal to moles per volume. So I could determine how many moles of rubidium hydroxide I have. Use the balanced equation to figure out how many moles of HF would be required. And then from there, use the C equals N over V equation again to figure out what the concentration of that is. So the first step, C equals N over V, or N is equal to C times V, so 0.3020 molar times, now we have to have our volume in liters, so 3 places to the left, decimal 0.3321 liters, and I get decimal 0.002942 moles of rubidium hydroxide. I won't round off yet because I'm going to use that in a further calculation. So far I'd be right here. I'd know how many moles of rubidium hydroxide I have. Next step, go from moles of rubidium hydroxide to moles of hydrofluoric acid by using the equation. And if we look, 1 reacts with 1. So 1 rubidium hydroxide reacts with 1 hydrofluoric acid. So our number stays the same there, even though our unit is different. We now have moles of hydrofluoric acid. So I would be at this phase right here. Then lastly, I know moles. I know volume. 20 mils is decimal 0.2000 liters. So I can now figure out number 3, the concentration of HF, by taking my moles over volume, 0.5015 molar. Okay, so basically 3 steps involved in figuring that out. I'll maybe pause the video, read part B, see if you can work through that and figure it out. Okay, if you had a chance to do that, NaOH and HBr, again it's a 1-to-1 ratio. On the assignment you'll be doing 2-to-1 ratios and maybe even 3-to-1 ratios. On the quiz I think I have a different ratio than 1-to-1, so be aware of that middle step there. So a 35 ml sample of NaOH is titrated to the endpoint by using 14.76 milliliters of HBr. The HBr is known to be 0.4122 molar. So we're asked to find concentration of NaOH. So the first step is to figure out how many moles of HBr you have. So C is equal to N over V, or N is equal to C times V. Concentration times liters, decimal 0.006840 moles of HBr. Then go from moles of HBr to moles of NaOH. So moles of HBr to moles of NaOH. We get the same number, of course, because it's a 1-to-1 ratio. And then lastly, I know moles, so moles over volume in liters will give me C, the concentration. So moles over liters gives you the concentration of NaOH. That's it. So vocab, we have neutralization reaction. Acid and the base react to make a salt plus water in general. Salt being the ionic compound that's formed, the cation from the base and the anion from the acid. Titration, the process of determining the concentration of an acid or base by carrying out a neutralization reaction. And equivalence point, the point at which moles of H plus and moles of OH are equal. Acid-base indicator changes color when the endpoint is reached, the endpoint hopefully being close to the equivalence point. The visual cue when the neutralization reaction has happened. So for example, methyl orange changes from orange to yellow at a pH of around 4.5. Okay, there you have it. That's the end of the booklet 19.4, acid and bases of the neutralization. Okay, see you again.